if I have a function, y equals f of x, and going from a to b again, however, the question is going to be, what is the length of the arc, not the area under the curve. The question is, how long is this little, think of it as a string, how long is that, it's what's called the arc length, how long is that particular part of the graph? And we are now to a place where we can answer this question, or we're going to answer this question. Now, it does involve an integral. However, it's a slightly different integral than just integrating the function itself, as we soon shall see. Actually, what we're going to use in part of this is we're going to use the mean value theorem, which is something that we talked about in Calculus 1. And what the mean value theorem states is that if I've got, here's another function here, y equals f of x. Remember, on the mean value theorem, it says that from A to B, there is a C somewhere in that range, A to B, such that f prime of C, so C is somewhere in here, probably right there. There's a C in there that, such that f prime of C equals f of B minus f of A over B minus A, which, remember, that's just the slope of the line from A to B. So that C, what that amounts to is the derivative of the slope of the tangent. So there's somewhere A to B such that the slope of the tangent line matches that slope of that line. And so that's why I was saying it's somewhere probably around in there, because, yeah, the tangent line would come in about there. So that's the mean value theorem. And that, like I said, that's kind of a blast from our past, so wanted to hit that with you. But that comes up when we're developing this formula, which I am going to try to go through. It turns out what you do is, here's this handout. Pass it on there. Do you want to pass it back? I've got it kind of, so you won't have to write all this out necessarily, but what we're going to do is take, for example, this one and divide it up. I divvied it up into 4 pieces. Okay, so what you're going to do is we're going to come up with these, instead of coming up with these curved increments, we're going to break it up into 4 little line segments, which, obviously those aren't exactly matching the curve, but it's a pretty good first estimate anyway. And, as you do more and more, it gets better and better. But the deal is, yeah, those straight line segments, of course, that, that's divvying it up into sub-intervals, x1, x2, x3, x4, is x4, but maybe I went too far on that one. A little far out there, but the picture on my handout's a lot better. Anyway, you get the idea. And so the arc length, which we'll refer to the arc length, the true arc length at y equals f of x from A to B as L. L is approximately equal to d1 plus d2 plus d3 plus d4. And so if we can come up with some value for those segments, then we've got ourselves an approximation anyway. the arc length would be approximately that. And then we'll talk about how we can make it much better. All right, well, since those are just line segments, the distance between points, because this is basically just figuring out that distance right there, is just figuring out the distance between this point, which is x sub 0 and x1, or x1 and x2. That's just the distance between points, which the distance between points, I remind you, is, on the handout there, x2 minus x1 squared plus y2 minus y1 squared. Yeah, you just take the difference of the x's squared plus the difference of the y squared, and then you square root it. It's based off of Pythagorean theorem. All right. Well, to kind of shorten this a little bit, another way we can think of it is, if I'm going between, that's using x2 and x1, but that's, that's just the formula numbering. Over here, it's x3, x2, or x4, x3. However, here's the way we'll kind of handle this, because isn't the difference of the x's here, we also know that as delta x. And then we can do the same thing, the difference of the y's is the delta y, and so that's the first thing I note there. If we do d1, it would be delta x1 squared plus, of course that would be the same for all of them, but delta y1 squared. Okay, now here's where the mean value theorem comes in. If you go to page 25 there, on my handout, you'll see that, well, delta y from our mean value theorem, I just erased, we can also say that f prime of c, what was it, difference of the y's over difference of the x's, from the mean value theorem, but here, couldn't we say that's the delta y over delta x sort of thing there? So anyway, each one of these, for delta y anyway, what I can do, if I solve this for delta y then is f prime of c times delta x. And so that's where the mean value theorem comes in. Since this is a continuous function, I can apply the mean value theorem to it, which on the mean value theorem says this, but if I alter it just a little bit, it says delta y is f prime c times delta x. I'm going to replace delta y1 by, well, it'll be f prime of c1 times delta x1. And then some nice things will happen. For one thing, if I do that replacement, it is replace delta y by this f prime c delta x from the mean value theorem. Do you notice what we've got here? We've got a common factor of delta x1 for d1. So let's factor that off, and that's 1 plus, you got to square both of those to be f prime of c1 squared. And so d1 is, since that's times, you can split those up, so it'd be delta x1, square root of delta x1 squared is just delta x1, times the square root of 1 plus f prime of c1 squared. Now, unfortunately, you can't do the same with that, because you can't, the square root of 1 plus something is not the square root of 1 plus the square root of something. Unfortunately, you can't do that, but that's as good as it's going to get there. But anyway, here's what all that, well, I did a little differently on the handout, but basically we can do these for all D1, D2, D3, D4, so I can come up with L being then, L then is approximately equal to this, the sum of, so if I can do this for D1, I can do it for D2, D3. So it'd be I equals 1 to 4 delta x of I times the square root of 1 plus f prime c sub I squared. So each one of these I can write that way, and so that's just pointing it out. And so L, you just add all 4 of those up. That's all that's saying, really, basically. All right, so how could I make it? I mean, that's a pretty rough estimate based on just those 4. However, how can I make it better? Well, do 10, right? Do 15, do 50, do 100. So if I move my I maximum, increase it to whatever I want to. So make that number more. Well, that's still going to be an estimate though, isn't it? How can I make it exactly match? Well, we've done this before. Let's run n to infinity. So to get the exact arc length, let's do the limit as n goes to infinity of this Riemann sum here, I equals 1 to n, delta x of I times 1 plus f prime c sub I squared. Okay? Which is what I have on page 26, middle of the page. All right, so yeah, if I just do n rectangles or n segments, that's still an approximation. But if I can do infinitely many of them, now I've got an exact value for it. Well, that's fine, and that would be hard to compute, that limit right there. I think we did one when we did a infinitely many Riemann sum thing. But what is this? What do we figure out, or what do we basically define this as? It's integral, yeah. So this stuff is just an integral. The limit of infinitely many of these sums here, that's an integral. And it's the integral, of course, would be a to b here. Just our limits. Remember, delta x, that's the same as dx. So that's my dx. So really the integral part of this is this. It's the square root of 1 plus the derivative of f of x squared. That is the arc length formula. So this is the length of the curve, y equals f of x, from x equals a to x equals b. All right? So, as I mentioned, it's not just integrating f of x. It is a little complicated, and it can, get really complicated really quickly, but we'll look at some that we can actually compute.
I was about to say, that could get really, really complicated.
Yeah, that can be really, really complicated. I mean, especially if you got a quotient as your function, but it is what it is. And, we can always use the approximate integration, since we just talked about that not too long ago here. So anyway, there are a few that we can handle, and here's our first one. So, but that's the formula. The square root of 1 plus the derivative squared. That's what you're going to integrate to find. That'll find that arc length. Interestingly enough. All right, so let's do it. So let's find the arc length for y equals x to the 3/2. And then we'll run x0 to 4. X to the 3/2. I'm not sure what that curve looks like. It's the square root of x cubed. That's not too bad then. X to the 3/2. Yeah, all right, so it looks like this. That's what y equals x to the 3 halves looks like. So I'm finding the arc length from here from 0 up to 4. So this is what I'm finding. Well, it turns out L is, and you might be saying, well, why did you pick x to the 3 halves? Well, you'll see why that one was picked. That's a good one to have here. So the arc length is the integral from a to b, square root of 1 plus f prime of x squared dx. There's another, that one's on the formula sheet, so that's another one for your note card. Formula card right there. So in this case, what do we got? A to b, so that's just the limit, 0 to 4. Square root of 1 plus, all right, so I don't put the function here, I put its derivative. So what's the derivative? Well, the derivative is 3 halves, x to the 1 half, and that's kind of why this works so nicely. So I substitute that for my f prime. It's 3 halves, x to the 1 half squared. Okay? All right, so what does that give me? Well, that's 0 to 4. Well, they won't all work out this nicely, but this one works out pretty nicely. You got to square your 3 halves, which is 9/4, and square your 1 half. What's 1 half? X to the 1 half squared. We'll just think of that. That's square root of x, square root of x squared. That's just x. Yeah, that's why x to the 3 halves works so nicely here. So I square 3 halves x to the 1 half, I get 9/4 x. Works out beautifully. They won't all do that, of course. All right, so let's see. How do I do that? So this is an integral. How do I do it? Always try U substitution first, and U substitution is going to work here. U equals 1 plus 9/4 x. We'll just have that be the square root of u. Now du would be, derivative of that would be 9/4 dx. So divide by the 9/4. So my du divided by 9/4, that's 4/9 du is my dx. So that gets me the square root of u times 4/9 du. Simple. Antiderivative, isn't it? Square root of u is u to 1 half, so the antiderivative would be u to the 3 halves. Got to do the reciprocal. Oh, don't forget the 4/9. But then evaluate that, but it's 4/9 times 2/3 u to 3 halves. That's the antiderivative here, because that's u to 1 half. With me there? Yes? It's just 8/27. U, but u is 1 plus 9/4 x. And we're going from 0 to 4. U to the 3 halves, I should say. It's an easy thing to do. Get that power. But it's u to the 3 halves, so it's 1 plus 9/4 to the 3 halves. Okay, so plug in our, I guess that's why I chose 4, because 4 plug in there. 4's will cancel, so I'll just have 10 right there. 1 plus 9 to the 3 halves, 10 to the 3 halves. Now, don't get carried away. If I plug in 0, I don't get 0, right? I get 1 to the 3 halves. So this will be 8/27 times 10 to the 3 halves minus 8/27, 1 to the 3 halves, which 1 to anything is still 1. So it's basically 8/27 times 10 to the 3 halves minus 8/27, which is a pretty good answer. But let me just show you how they will probably write that answer. So that's okay. 10 to the 3 halves is the square root of 10 cubed. Well, you could say it's the square of 1,000, but they'll still say something a little bit better than that, because 1,000 is 100 times 10. That's 10 squared root of 10, yeah. That's how they would probably write that. 10 to the 3 halves is 10 squared root of 10. So just FYI, I don't necessarily have to have that form, but just be aware. All right, any questions on that? Is that okay? All right. Now let me show you this one. This one's really tricky. It works out nicely, but it's sort of hard to see it if you're just doing it on your own here. You may not see how this works out so nicely, but that's what I was going to show you, how this one works. All right, so find the arc length here. Y equals x cubed over 3 plus 1 over 4x, and that x is going to run 1 to 3. Yeah, that doesn't at all look very nice, but for derivative purposes, I'd probably write that as 1/3 x cubed, right? And then this is plus 1/4 x to the minus 1 would be a better way for derivative purposes, right? I believe so. All right, so with that in mind, the arc length then is the integral from a to b, so it'd be 1 to 3, times the square root of 1 plus derivative of that squared. All right, so yeah, that's what I was saying. The derivative here, easier now to do. The derivative would be 1/3 times 3x squared. It's just going to be x squared. And then it'll be minus 1/4, bring down to minus 1, right? X to minus 2. Right? So the derivative is x squared minus 1/4 x to minus 2 squared. Yeah. So arc length is 1 plus the derivative squared. So that's what I've done here. Yes? Okay. Well, let's just go ahead and square that derivative stuff out. So x squared minus 1/4 x to minus 2 times x squared minus 1/4 x to minus 2. Pull it out. So you have 1 plus, and then you'll have x squared times x squared is x to the 4th. X squared times minus 1/4 x minus 2. What's going to happen there?
Minus 4.
So I've got x squared times negative 1/4 x to the minus 2. Yeah, something really nice happens. The x squared and x minus 2, you're going to add the exponents to get x to 0. That's just negative 1/4, isn't it? So that times that's just negative 1/4. That times that's negative 1/4. And negative 1/4 x minus 2 times negative 1/4 x minus 2. That's just a positive 1/16 x to the minus 4. All right, so good there? Now, that and that you might note here. So this is this right here, because this is important to note here. So when I multiply this out, I get x to the 4th minus 1/2 plus 1/16 x to the minus 4. And the reason I write that is because, not just because I'm going to simplify it, but just note that, okay? If I square that, that's what I get. All right, now, I do have 1 plus that though, right? And so what I wind up with here is the square root, and let's write it this way. That'll be x to the 4th, then the 1 minus the 1/2 is positive a half, right? Plus a 1/16 x to the minus 4. Which still looks rather ominous. However, you understand that, okay, so let's look at this. So I've got x squared minus 1/4 x to the minus 2 squared. That equals, it was x to the 4th minus a half plus 1/16 x to the negative 4. Now why do I mention that? What do you see here? I don't quite have that, but I have just about the next best thing. I've got x to the 4th plus a half plus x. So what I'm saying here is I've almost got this, except it's a plus half instead of a minus a half. So how could I factor, in other words, this? It's not going to be x minus 1/4 x to the minus 2 squared. What's it going to be? Isn't this going to be the same as that except plus in between it? Yeah, this right here is x squared plus 1/4 x to the minus 2. And so that's why this is such a strange looking function. I don't think we've ever had quite that same function before. But it works out so beautifully here because when you do all the math here, this turns into the square root of, and so it's x squared plus 1/4 x to the minus 2 squared. So it's a minus instead of a plus there. Sneaky, huh? Because now what? Well, that's beautiful because you got the square root of something squared. The square root and the square are going to cancel out there. And so you got L equals just the integral 1 to 3 of just x squared plus 1/4 x to the minus 2 dx. Get rid of the square and the square root. So you don't have that square root stuff anymore. And it's just a simple antiderivative, right? The antiderivative of x squared is 1/3 x cubed. The antiderivative of 1/4 x to the minus 2, well, you keep your 1/4, add 1 to the negative 2 power, you get negative 1 power. So you're going to divide by the negative 1 here. And then you're going to run it 1 to 3. So we got 1/3 x cubed minus 1/4 x to the minus 1 from 1 to 3. So it just turns into a nice, because you got rid of the square root basically, it's just a nice simple antiderivative. Question? Plug in the 3, so it's 1/3 of 27, that's 9, minus 1/4, 3 to the negative 1, that's 1/3, right? Plug in the 1 to anything's 1, so you got 1/3 minus 1/4. So it's 9 minus a 12 minus, is that 1/12? It's 9 minus 2 12, 9 minus a 6. 8, 5, 6. Or some equivalent thereof. Yeah. How's that?
Is that 85/6 or 8?
8 and 5, 6. Yeah, because this is 9 minus a 12 minus, that'll be another 12. So it's 8 minus 2 12s, or 8 minus a 6. And 8 minus 1 6 is 8, 5, 6. That's how I came up with that. But you can just punch it in. But, what would that be? 40, 53, 6. Something like that. Question? Is that okay? You got it?